Number 1. This diagram represents a wave with a frequency of 1.1 Hertz. What is the speed of the wave? Very simple equation. Speed equals frequency times wavelength. We have the frequency, we have the wavelength. There's nothing more to do there. Number 2. What is the frequency of light if its wavelength is 4.70 times 10 to the negative 7 meters? So now we've got to find frequency, but we're going to use the same equation with a slight twist. Because we're dealing with light, we need to deal with the speed of light. In your reference table, on the very first page, it says the speed of light in a vacuum, it's also known as c, is 3 times 10 to the 8 meters per second. Einstein's famous equation, E equals mc squared. The c is the speed of light. So the speed is 3.00 times 10 to the 8. That equals frequency multiplied by the wavelength, which is 4.70 times 10 to the negative 7. We have our frequency. Sorry, we're trying to find out our frequency, but we have the speed, we have the wavelength. There's a little bit of mathematical manipulation you need to do here to find frequency. And remember, if you're dividing by either one of these numbers, you're going to want to put them in parentheses. Number 3. The diagram here looks almost identical to number 1. It says if the frequency is 25 Hertz, what is the approximate speed of the wave? So speed equals frequency times wavelength. We have the frequency. Now, immediately you want to use 11 meters as the wavelength. But 11 meters is actually 2 waves. So there's something you want to do with that 11 meters before you substitute it into the wavelength. But we have the frequency, and now we can just figure out the speed. Number 4. The diagram below shows a ray of light passing from air through a piece of glass and then back into air again. And it says if the angle of incidence, this is your angle of incidence, it's the angle between the incident ray and the normal. The normal is this dotted line that's at 90 degrees to our surface. Now if you look at that diagram, if the light goes in from the air into the glass and then it comes out into the air again, and when it comes out it's going the exact same direction it was going before, they're saying which other angle is also equal to 60 degrees. And I think just looking at the diagram and being logical about it, what's going to have the same size as 60 degrees? Is it W, X, or Y, or Z? Number 5. A ray of light traveling in water enters a different medium. If the incident angle of the ray is 47 degrees and the angle of refraction bends towards the normal, what does this reveal about the index of refraction of the medium? I'm going to use this diagram for question 4. Because here you've got light traveling from air into a more dense medium. And when light travels into a more dense medium at an angle, it always bends like this. It bends towards the normal. Okay, the normal is our dotted line. You can see the light is actually bending towards the normal. So if it goes from less dense to more dense, it bends towards the normal. If it's going into a less dense medium, like it's doing over here, then it bends away from the normal. So you can say in towards the normal, out of a less dense medium. If it goes into a more dense medium, it bends towards the normal. If it goes out of a more dense medium, it bends away. So using that information, if we are dealing with light traveling in water and it's going to bend towards the normal, remember if it goes into a more dense medium, it bends towards the normal. Which medium has a greater optical density? Okay, and it must be something with a greater optical density. Number 6. Blue light. Let's change the color for this one. Blue light and a sound wave travel through the air and they enter a glass block at an angle of 45 degrees. So let's say there's our 45 degrees. There's our blue light. Our blue light is going to bend when it goes into the glass. And if we had light, light is also going to travel and it's going to bend. Sorry, not light, sound. Sound's also going to bend. It's going to change direction when it enters the new medium. The sound is actually going to do this, but we don't need to worry about that. We just need to worry about the fact that light travels fastest when the medium's got the lowest density. Like the speed of light is 3 times 10 to the 8 when it's in a vacuum. That's the lowest density. However, if this is our sound travels fastest when the medium is more dense. Like in steel, sound travels about 100 times faster than what it does in air, for instance. So using that information, that sound travels fastest when the medium has a low density, and sound travels fastest when the medium has a high density, I think you should be able to figure out what's going to happen in that case. Right, number 7. This has got to do with the Doppler effect. So an object produces a sound of a constant frequency, and there's an observer that's hearing that sound. If there's a relative motion between the thing making the sound and the observer, what's going to happen is these sound waves are going to bunch up. So the frequency is going to go up. Frequency and pitch are basically the same thing. So frequency is going to go up, the wavelength is going to get shorter. However, if the object that's making the sound is moving away from the observer, or the observer is moving away from that object, what's going to happen is those sound waves are going to, I'll draw it here, they're going to spread out. And when they spread out, wavelength gets longer, but the frequency or the pitch goes down. Number 8. Which best describes different mediums in which the speed of light and sound is greatest. So for number 8, just remember what I said earlier on, is that light travels fastest when the medium has got a very low density, like a vacuum, and sound travels fastest when the medium has got a high density, when the particles are closely packed. And with light, we're actually talking about the optical density. With sound, we're just talking about the basic density of the object. I hope this helps.